It's my pleasure to introduce to you Holger Regenbrecht of the University of Otago in New Zealand. Holger is a professor at the Department of Information Science at the University of Otago. He did his PhD at Bauhaus University. That's where I met him. So we have been at Bauhaus University in Weimar together for a couple of years. I was media science and you were architecture, but Holger was doing virtual reality and augmented reality there already. So he's interested in that field since many, many years. You see the title of the talk, Voxel-Based Mixed Reality, is about mixed reality still. Between Bauhaus University and going to University of Otago, he was also at Daimler Chrysler Research and Technology in Ulm, doing also AR and VR there for the automobile industry. And he's going to talk about voxel-based mixed reality now. So Holger, it's yours.
Oh, thank you very much. Thank you very much, Oliver, for the nice introduction, and thanks for having me for that talk. Actually, I hope at the end of this talk you're convinced that voxel-based mixed reality is not a bad thing to do, and that you might give it a shot yourself. And I based that talk on a recent talk I gave at the ISMA conference last year in Nantes in France. The International Symposium on Mixed and Augmented Reality, but I added some more stuff to it, so you will see. So I structured it in a way that I give a very, very, very brief overview of our lab, so that you roughly know where we are and what we are doing. But I won't do that for much too long. Then I will talk about voxels. Of course, this is what this whole talk about is all about: voxels, and again a little bit about future work. So the core part is actually about voxels. Let's start with our lab. So this is where we are located, and then I chose a map which you are familiar with, which has Europe at the center, and at the very right-hand side here, over here, you see New Zealand, and it has the North and the South Island, and we are actually at the southern end of the South Island in the beautiful city of Dunedin. And Dunedin hosts the New Zealand's oldest university, but in European terms, it's not that old. I mean, the university is just 150 years old. It's a very research-intensive university. It's of medium size. It's about 20,000 students, but is one of the main employers in the city, because the city itself is only 123,000 population. So it's really a student city, Dunedin. So we do have actually two main computing departments, the computer science department and the information science department. I'm with the information science department, and we do more what you might call the classical informatics or the applied informatics programs. So these are our main research areas: data science, autonomous systems, information systems, software engineering, and some sort of intelligent computing and networking, which also includes artificial intelligence. And so I'm with the Human-Computer Interaction group, and so we do mainly do technology in the realm of human-computer interaction. So this is our lab, and it's co-lab by myself and Tobias. And Tobias Langlotz, perhaps some of you might know him. He actually studied with Oliver back then at the Bauhaus University in Weimar, and then did his PhD with Dieter Schmalstieg in Graz, before he came then, perhaps I think 3 years ago, to Otago. And since then, Tobias and I, we lead our little group and lab. So it's not a very big group. So we're about, at the moment, I think 6 PhD students and perhaps another 4 research students, plus the 2 of us. So it's a small group, but we have a nice lab environment, and we do kind of couple of a wide range of projects. I come to that in a sec briefly. Mainly what we are doing is two kinds of projects. So one is either more what I would call scientific or experimental work, where we try to test some ideas or assumptions or hypotheses, and then we do an experimental design, build a prototype, and in the end we run an experiment and interpret and discuss that. Or on the other hand, there's a problem to be solved, And again, we develop a system and then we test it and we try to disseminate it into the field. So the main point here, what I wanted to say, is that all of our students, all PhD, research, masters, honors students, they have to do always two things. So they develop a system, a prototypical system, and they have to evaluate it. So there's no student which just does only one of those two things, which can be a little bit challenging, because as you can imagine, most developers are not too keen to do user testing. But this is what we do, and so all of our research is actually always bundled in that way. Finally, about our lab, this is what we are specializing in. Our main research themes are around mixed reality, so augmented reality and virtual reality. So this is, as Oliver said, so I'm doing that for 20 odd years, virtual and augmented reality. So I'm a one-trick pony, I would say, in that field somehow. You do also, that was what Tobias brought into the lab. We do mobile systems research, in particular ubiquitous and pervasive computing, and we do presence, so sense of presence and telepresence research, and in particular we are interested in all those overlapping areas between mixed reality, mobile systems, and telepresence. And you see, the pictures tell roughly the story. We do kind of very different research, from using head-mount displays or to tangible interfaces to whatever. And sometimes we are lucky, and then we can bring stuff into the field, like that augmented reflection technology system for stroke rehabilitation, for instance, or some wheelchair simulators or something like that. So these are the moments where we think, yeah, we're doing something really right. So, but now I'm coming to the main topic, which is voxels. So voxels are, as you know, it's not a new concept at all. So if you're all familiar with the computer graphics textbooks, and you will find voxels in those. And voxels have been of interest to many researchers for decades now, but they haven't been used too much for real-time interactive graphics, because they are computationally expensive. So 2 years ago, I went to reality, which is probably the biggest virtual reality conference, and that was held in France. Actually demoed something there, and that was, when you look at the picture down here. So they used to connect RGBD, so RGB and depth sensing camera. So with that one, they scanned the environment, and in that environment, so a user was using an Oculus Rift head-mounted display, and so the point cloud from the Kinect was mapped into that space, and the user could walk or look around in that space, and could immerse him or herself into that point cloud. And there is a little video clip on that, and I hope you will see it. And that was shot through the head-mounted display. So what you see here is the environment. You see a real table, a point cloud of a table. That's the table. User can look around, and with embedded in that environment is also a CAD model, a computer-aided design model, or a 3D model, if you want, of a push bike, of a bicycle. So the handlebar of the bicycle, and you see another person standing there, and there's another table with a edge. So that was the demo, which made me what are that? There's no real name for it. It's not video see-through augmented reality. It's not optical see-through augmented reality. It's not spatial augmented reality, which Oliver wrote a lot about. It is kind of an outside-in augmented reality, or video-mediated augmented reality. But there's especially with that Dassault demo, Dassault Systems demo, there was a little bit of a problem, or actually a big problem, with coherence. So what we saw within that space were actually two different data representations. So one was a point cloud, and so that point cloud was generated directly from the Kinect data. So they just took the depth plus RGB points and translated them into 3D space. And on the other hand, they had that CAD model of that bicycle in it, which was just introduced as a meshed, triangulated model within the scene. And so what it was lacking was really a coherence between the two spaces. So either you thought the environment is the real thing with the point cloud, which you saw the table and the chair and the other people and your own hand and so on and so forth, or the bicycle, but they did not really fit together. So the question was whether one could use a unified coherent model for both, which might combine some of the advantages without sacrificing too much. So the idea is the old idea of using voxels. So you divide up the space in a regular grid, and you try to voxelize everything to have a one coherent environment. And that is what we in the following years now did. And so I come back now just to explain what voxels are in particular in comparison to point clouds, just as a kind of a recap. So let's start with pixels. So pixels are actually color points in a regular grid on a 2D plane, right? And the trick with the pixels is that they appear as gapless representations. Even if the actual light emitting elements, as you know, can be 3 or 4 elements per pixel, but when we look at an image or a monitor, for instance, we see that as a gapless representation of an image on a plane. So if you take that into the third dimension, then you get a gapless volumetric pixels in a regular grid in space. So, and the main difference to point clouds is a point cloud, every point in a point cloud would have a 3 float x, y, z representation plus a color. So the points can be everywhere in that floating point space. But with voxels, they're always in a regular grid. Right, so they're predefined grid positions. But again, we want to achieve the same effect, so a perceived gapless representation of those volumetric pixels. So if we can convert everything into that kind of representation, then so is the hope we get a higher coherence of the scene, and with that a higher believability of the whole mixed reality scene. So to achieve that, actually, we built a prototypical system, and our hardware setup looks more or less like this. So we do have a user acting in real space, in that case at a table, and that user is wearing a head-mounted display. In our case, it's an Oculus CV1 head-mounted display. The head-mounted display is tracked by 3 Oculus cameras in space. And up here on that gray frame, we do have a Kinect version 2 RGBD sensor, slightly angled towards the user to capture what is in that space, what is visible in that space. And the user looks through that space with the head-mounted display. So the dimensions of our voxel space is quite limited. So we defined it as a 2.5 meter cubic space. And here you see the frame again with the Kinect camera, and which watches that, observes that voxel space. So everything we do is actually we are voxelizing everything which we can see in that voxel space of that size. So to give you an impression how it looks like, let's say we put a chair into that cubicle space. A chair would be look from the RGB component of the camera like this, and if we combine that with the depth camera image data and voxelize all the points, then we get a representation which looks roughly like that. So this is the actual voxelized version of a chair in our system. But to come to a coherent scene, like in the example of Dassault, where they introduced a bicycle, we also want to introduce voxelized CAD models. So what we do is we do the same thing to the CAD models. On the left-hand side, you see the chair modeled in, I think in that case, in Blender. On the right-hand side, so you see a voxelized version of that same chair. So what we do is we degrade actually the quality of the model. This is a finely meshed triangulated model of a chair, and we voxelize it again. So we lose quality, but with the intention to increase coherence in the mixed reality space. So when we look at it from the Kinect camera perspective again, then we see roughly like that. So everything is voxelized in that environment. So in that case, the user and the chair, and we background subtracted all the rest to get rid of all the elements which are not necessary for the scene, like the cabinet and the background and so on and so forth. And we introduce, as you can see here, the CAD model of the chair, right? So to give the user the impression that both objects are actually real, and you have to probe it to find out which one is real and which one is virtual. So that's the coherence test, so to say, for us. I come to that in a second. So what we also did, we introduced a virtual mirror scene. So that user, now the upper left image, that user is now again wearing the head-mounted display in that space. We have a table there with some props on it. The Kinect is voxelizing everything. And we introduce a mirror plane exactly here where that frame sits. And down here, you see what the user is seeing. So she is seeing herself in that virtual mirror. And this is a side scene which normally is not seen by anybody, or certainly not by the user. So, and you see, when you have a closer look at the table, so there are real objects on the table, but also virtual objects on the table. So I show you now a short video clip of a user which, for the first time, and that was an installation I did at our with our collaboration partners at the University of Oslo, at the psychology department there. So I just installed the system there, and that was the first user who actually really tested the system. So what you see here is the first-person view of the user, plus that inset shows a camera view from the front of the frame, so to say. So that person is now looking and trying to virtual voxel walking in. I come to virtual characters later, and see what is happening here. So the person now is trying to find out what is real and what is virtual. So are these objects there near the ceiling, are they real or not? And the only way to test that is actually to ask others about it, right? As you can see. Also, on the table, you see, in reality, there's only one object on it, and in the virtual reality, there are actually three objects. So two objects are virtual, and one is very similar. So now the user is what it can be seen of himself in the environment. What was actually in the beginning, it was a bug in our implementation, but we used it as a feature because it's a very interesting experience. So the Vox frozen now, and now you snapshot of the Vox self as a front voxelized character, because we are using just one camera in that one Kinect in that scenario. So you walk around yourself, and that's quite a scary experience actually, to see yourself in that kind of environment. So the question is, so what are all the factors you have to take into account if you want to build a coherent mixed reality voxel environment, even if it is as coarse as you see here? So I'm going through a number of the main factors, not considering all, but if you want to know more about it, especially the ISMAR paper will have on that. So the first is, of course, the placement of the space and the Kinect camera and the resolution you can achieve or you will get from the Kinect camera. And the Kinect, if you voxelize everything, of course, you get a variable possible maximum resolution. Closer to the Kinect sensor, you get a higher resolution, and further away from the Kinect sensor, you get a coarser resolution. So a point cloud would actually show what is there. So that's the advantage and the disadvantage. So it has a variable resolution over space, but you get all the resolution which is there. So voxelization, you get the uniform representation in space, but you have to optimize for a certain resolution. So, and you don't have to read all these numbers here, but in the end, when you see it visually, when you inspect it visually, like in that slide here, you see on the left-hand side, it's a 5 millimeters voxel grid resolution, and on the right-hand side, an 8 millimeters. So in that case, because of that sampling, particular sampling of the Kinect, the 5 millimeters look actually worse than the 8 millimeters in our given volumetric space and the given placement of the camera, which we defined beforehand a priori. So and of course you have a trade-off range. So what can you render in real time anyway? So I will come to that. So in the end, for most of our applications or prototypes, we opted for an 8 millimeters resolution, but you can control that, of course, as you can imagine, in a certain range, depending on what you get from the sensors. In our case, what you get from the Kinect RGBD camera. Second main thing is, and this is always a big issue in mixed reality environments in general, is how do you place the lights and shadows so that virtual and real objects are lit and shadowed in the same way. In our case, because that was not the focus of our work, we placed static lights in the real environment as well. So we took the office lights, we measured where they are, and we placed virtual lights at the same position, which gives us with some shader functions a nice enough shadowing. But there's a lot which can be optimized. The nice thing about voxels, because they're so coarse in our case here with 8 millimeters, or even that is a 1 centimeter example, I think, is that it is not, you don't have to go for the highest possible fidelity in lighting and shadowing, because you wouldn't see it anyways. So I will show you you will see that in the next example when it comes to the spatio-temporal noise. So this is actually the main aspect you have to simulate if you introduce CAD models into the real world voxelized space. So we have two objects here, which you can see. So this is that toy horse, which sits on the table. And then we have that toy doll, which is a CAD model. And we bring both into the same space. And I'm playing that now in a loop here. What you can see is that we apply the same noise, or we apply simulated noise to make it close as possible to the real Kinect approach before. Both looked like the same. So it would be really hard to tell toy or CAD object, or whether it's the real or the virtual one. And that's the whole trick about space, right? Expression that virtual and real in the same. So theoretically, well, because we have CAD models and we have voxelization to apply to it, so could actually vary the grid resolution as we like, right? So we voxelized some examples here just for you as a demonstration. So let's say from a 16 millimeters grid on the left-hand side to 1 millimeter grid on the right-hand side. So there are 2 points. So one is, do you always want to have the highest possible resolution, and what do you trade in for it? In particular, you trade in latency and frame rate. And what is actually what is the just noticeable difference? When do you reach that point when it is believable? I would even argue for that even the very coarse resolution of 16 millimeters, or even on the left-hand side, would be kind of Minecraft resolutions. You don't need that always the finest resolution, and I'll come to that in an example at the very end. So what we because I said to you, we opted for the 8mm resolution, and with that kind of resolution, between 8 and 6mm, say, so we can render about 500,000 voxels in real time with almost no latency, so, or at least not noticeable latency. So that's okay, and that's on the standard, off-the-shelf brick and mortar PC. With a GTX 970 card or something like that, so it's nothing really special. But meanwhile, we are using better cards and computers. Okay, so that is for objects, for CAD objects, and for real objects in the scene. But as you could see in the Oslo example, there's also characters coming into the scene, and it's actually a very powerful tool with that kind of approach. So we can introduce voxelized characters, and we can have live characters, or we can have recorded characters, or in the future we might even have generated characters in the scene. But what we have here now is recorded and live characters. And I'm just showing you a short video clip about that, which also depicts our current setup, which is we use now between 1 and 4 Kinect cameras in our setup. Here we are. So there's our student Noel sitting there controlling the system. You see a desk with a helicopter. And so you see we have one other Kinect we are not using for that particular demo here, and 2 more Kinects. And so the whole either always or better voxel. So here these are recorded characters, and they are individually recorded and then put together in the virtual scene. And they are placed in 3-dimension that space, and so you count them, and even if you captured from one side, you get the impression that they are real, have spatial appearance, right? So if you want now to find out which are real and which are recorded characters, it is actually quite hard. I mean, you really have to probe that. So you so not everybody would do that, and you see here, so there are 2 recorded and 1 real character in that scene. But also it's interesting with that kind of solution, and because so you take for real what that kind of that environment, so you respond to that. In that case, a recorded character is handing over a piece of paper. You have to take it. You see, that's a similar scene to the before, and as you can see by the noise in the scene, this is actually a recording too well in that scene. Me entering that. So you see, that's quite a powerful tool to have characters or avatars in a scene which are very coarsely rendered, but have a very lively and believable appearance. So when you compare that to highly realistic triangulated meshed avatars, there's quite a difference. But these characters can play a role in a lot of applications, especially for our cases. Finally, what we get is with, so to say, for free with voxels. So we have a very coarse representation here of some voxel, just to illustrate the case. So actually, starting with occlusion. So normally in mixed reality, occlusion between the real and the virtual is always a problem, right? So normally in video see-through augmented reality applications, for instance, normally the reality is in the background and all the virtual objects are in the foreground. Or you can separate, let's say, your hands out of the real world and put them into the foreground, and then all the virtual objects would be in the background. But what you really want is actually a correct occlusion between real and virtual. So in the voxel world, you get that, so to say, for free, because all the all the pixels are voxels, are volumetric pixels in space. So naturally, all the voxels in the front are occluding the ones in the back. So you get a for free occlusion handling with the voxels. Of course, it's computationally expensive, but it can be done, at least for the very coarse resolutions at the moment. And also, what you get almost for free is interactions between the real and the virtual. Let's say you have a real hand and a virtual toy, because every voxel can and is a collider, and collides with the voxels of the real and the virtual. So you can have all kinds of interactions between all those voxels, and with that you can implement a meaningful interaction between those, and manual interaction between those domains in a more realistic or more versatile way than before. So I just went through the main factors. There are more, but these are the main factors we see for the mixed reality voxel space. And we evaluated the whole thing in a number of smaller user studies at our place at Otago University in Dunedin, as well as in Stefan Müller's lab in Koblenz in Germany, as well as with Thomas Schubert's lab in Oslo in Norway. And what we used here as an example is we used mainly events where people go there, anyway. And we have a so-called photo booth application. So where you go there, like a photo booth on the railway station, where you go and get your passport shots with your best mates and some props. We do the same here in 3D space, and with that one, we tested the believability of our application, and it worked. And we used a voxel resolution of 8 millimeters. This was mainly what you saw before. And it was believable for actually almost everybody. And sometimes even it was believable to a degree that people do not even wonder about whether another person walked into the scene, even if that was a virtual recorded person, because they really thought it belonged to that scene. So before I come to the final words about future work and what we are doing at the moment, I want to summarize what mixed reality voxel can be. So I think voxels can be a serious rendering option for mixed reality, even if they look that coarse and not very sophisticated at the moment. But even that can be an advantage for certain applications. So I guess we will see more and more of that. Of voxel rendering in interactive computer graphics in the future. The main point for mixed reality is that coherence is key. So it has to be a coherent mixed reality environment. And we can achieve that with the voxelization of everything. Everything is voxelized, so therefore there is coherence. And finally, to do so, actually less can be more. Actually, without denying all the good work which is done in photorealistic rendering, but this could be an alternative adjunct method of doing mixed reality. So by intentionally reducing the rendering quality and using voxels for that purpose. So the final brief part of my talk is actually about what we are doing currently and what our future applications will be. So while we were working on the system in the very early stages, one of my colleagues from the psychology department, Ted Ruffman, saw what we were doing, and he was very interested in it. So our application was not even finished, our prototype wasn't even finished, but he was very interested in using it. And his application scenario is a study on racist attitudes of children towards other people. So they did a study with Asian actors and with Caucasians, with white actors, and wanted to test whether children would behave differently to when interacting with one of the two or both races. And so they tested it, for instance, by dropping a pen and then observing whether a child would pick up that pen for that person and would help that person, and so on and so forth. The problem with those studies was that with the actors, that even if the actors are acted very professionally, the children always developed immediately, an emotional relationship with the actor, so with the person and not with the character they wanted to represent. So what Ted Ruffman and his group were looking for were a way to control the level of realism of that character. So now our voxel-based mixed reality system comes into play. So what we did here is we recorded first different resolutions of characters with our setup, and then they were tested for their believability and what is the just right resolution. So coarse resolution, which is seen as a character in the scene, that was tested beforehand. And now at the very moment, they are running a study with 100 participants, actually, that will be finished this week. And these participants are children, and they are presented with those scenes of virtual characters, voxelized and recorded in different scenes, and then they're doing their study. So this is happening at the moment, and it's a very helpful tool for them. And the main aspect here is, I repeat, that is the controllability of the degree of fidelity here. The second realm of applications, and that's actually where we came from when we thought about that, applications for that kind of technology, is body perception studies. So how would you perceive yourself, let's say in that case in a virtual mirror? So this is actually it's a point cloud rendering, but we will change that into a voxelized rendering. So where you can change the body shape and your how your limbs move and so on and so forth, and that can be used for different scenarios. In that case, it is for as I said, for body perception, especially for anorexia nervosa, mainly for young females, but also can be used for stroke rehabilitation or physical rehabilitation, and so on and so forth. So this is what we're working on. It's a very nice tool to apply our technology to. The second aspect is, and I'm just sketching that here with myself 3 times voxelized, is telepresence. That's an obvious candidate to use those mixed reality voxel environments for. So we at the moment we're developing that, and that will be tested by the end of this month with one of our European partners, and so we will see whether we can enhance the telepresence experience by using voxels instead of pixels or avatars. And finally, one big application area is actually using voxelized avatars, controlled voxelized avatars in manufacturing planning applications, where we either interactively or simulated, you try out reachability, for instance, in environments or workload issues, and so on and so forth. That's also in planning with 2 actually European partners in the end. Very recently, yesterday, and last week, you might have seen that actually Intel, yes, I think it was, their new 3D True View technology. So they are also using voxels for that. And if you have a lot of money to spend, and you have a lot of good engineers around, then you could do something like that. So in that case, they are recording NFL games with 38 high-tech cameras in a stadium, and each of the cameras is connected to a dedicated server. So they have 38 servers, and they are processing all the data to voxelize certain scenes in space. And so you can actually view around certain aspects fractions of seconds later when they happened. And so you see where it's going. I mean, not only the controllability of voxels is key, but if the resolution increases, and if that follows Moore's law more or less, then we can expect photorealistic, actually, voxel representations probably within the next 10 years. And Intel is actually presenting here where that stuff is heading to. So that brings me actually to the end of my talk, and I thank you very much for your attention. And these are some of our students, of course, voxelized as always. And if you have any questions, I'm here to answer your questions. Otherwise, just send me an email or have a look at our webpage, www.HCI Otago ACNZ, to see what else we are doing. And we are always keen to host good and talented and bright and motivated students. We had a lot of students from Europe over there, and they all enjoyed it. So if you are interested in what we are doing, so just contact us. And thank you very much.
Thank you. Questions?
We have one remote question actually sent to us via email from Patrick Saal, University of Magdeburg, and he asks, or he wrote, great talk so far, there is no built-in function to do volume rendering in Unity. Do you use an own development? If so, which technique?
Yes, good question. So no, we used voxel rendering within Unity, but that limits that it has certain limitations. So you can probably render a couple of 10,000 volumetric points with that. No, we implement our own shaders for that and put them into Unity as a function call. So I mean, yeah, actually Unity is only used as the framework around to handle the the views for the head mount display and stuff like that, but the whole rendering is done by our own shaders.
Okay. More questions?
I see that you use Oculus Rift a lot. Do you also use Microsoft HoloLens or an augmented reality glass?
Yes and yes. So we use Oculus Rifts mainly because they work well with the Kinect. We also have an HTC Vive implementation, but that interferes with the Kinect, so we can't use it for real-time voxel stuff. But we can render the voxels as well with an HTC Vive in an Unreal environment with a different shader actually. And we also used it with the Microsoft HoloLens. But mainly we are focusing on the Oculus Rift at the moment, so as our main device. But it is more or less device agnostic, what I would say, because we are using the Unity or the Unreal framework for it. So the whole view management is done by those technologies, and we just put in our own voxel shaders and our own data management and so on and so forth. Yeah.
Okay, more questions? Well, a principal question, what's the advantage of a voxel-based representation versus a triangular-based representation versus an image-based representation, which you could all get from the data that you get from the center?
Yep. So I think the main advantage is, and we did not exploit that really, right? Is that you have a unified data representation for everything. So that's always the voxel, and so what you can actually use, you can use a lot of techniques which we know from 2D images, or also which we know from actually historic voxel research, and we can now use it because now we have the computational power. For instance, for data storage, you can just use octree models. It's very simple and easy to use. Or you use compression algorithms from which you know from images or video streams. Or what I said, if you use for the interaction or for the occlusion techniques, right? You get all these advantages of the voxels actually for free. And so in the end, yes, voxels are more computationally expensive, especially if you go into the high-res world of voxels. But on the other hand, you gain a lot because of that very unified and very simple data model. I mean, it's that is the beauty. The simplicity of the model is probably the beauty of it. On the other hand, you get the coarse representation, which is not, you get better results with other techniques. So yeah, it's a little bit of a trade-off question, but yeah, we try that approach now and think that might lead to good applications and good scenarios in the future, or even now with that coarse stuff. But yeah, but there's a niche for that, I would say.
But if you, for example, go for classical triangle-based representation, I mean, you have also coherence, you have occlusion, you have mesh compression, the computation is in real time. The coherence aspect I didn't really get. I think the reason why this seems to be more coherent, where people cannot tell the difference between real recording and the CAD model, is that you decrease quality quite a bit by voxelization. You get the same kind of noise, and then it's probably harder to tell what's real and what's virtual.
That's true. That's true. You're absolutely right. So you get. By decreasing the quality of the model, you get the coherence. But the point is that you have the reality really at the same quality as the CAD models. I mean, that's the point. And I see the point that if you want to lead that, let's say I wanted to do it highly realistic. No, I couldn't. But at the moment we are at I think with the I have to, but let's say with a 1080 Ti card, with a single card in the computer at the moment, we could probably render about 1 million voxels in real time with, let's say, a latency of 40 milliseconds or something like that. So actually, you are getting to the limits if you want to very fast if you want to do photorealistic stuff, definitely. But if you want to have, let's say, a cheap version of a coarse representation but coherence, then probably that's the way to go. Or you say, okay, in the foreseeable future, we will have all the computational power in 10 years' time. So why would I bother with any kind of optimizations otherwise if I can have everything from voxels plain, so to say?
Did you experiment with just getting your point cloud data from the sensor and having real-time triangulation and use meshes instead of voxels?
Yep. Actually, we do. I have a little bit of an echo on it, but it doesn't matter. Actually, in the 3 and 4 Kinect setup, our setup is based. We have one Kinect connected to a Windows machine and 3 Kinects connected to a Linux box, and on that Linux box actually runs Stefan Beck's multi Kinect server. And Stefan also implemented a very nice triangulation of voxels. So we did not even have to implement it. We just used his one, his triangulation. And that works pretty well for a certain number of voxels. That's great. And he achieves really great results. It has a little bit of that kind of artifact problem. So, if you get slight artifacts, for instance, around the eyes or around the face, then that's immediately visible because you expect from a high quality meshed rendering, you expect photorealistic reality. From the voxel model, you don't. I mean, you just take it. But we have both implementations. One we did ourselves, the other one we got for free from Stefan Beck.
I also was interested in the first study you mentioned with the kids, see how they react to different races. Do you think it matters if you do such a study, whether you have real actors or these kind of virtual characters, where kids in particular probably take this more like a game, like a video game, and would not react in the same way as they would react when they have real people sitting in front of them. So if somebody drops a pen and you have to find out if the kid picks it up or not, and the kid doesn't, maybe this has to do with the race, but maybe more with the fact that the kid knows this is more like a video game.
Good question. I don't have the answer because it's not my study. So those colleagues came to us because with the actors, they were unsuccessful and they replicated the study with our system. So that's a kind of an indicator. Yeah, perhaps that aspect works better. And I because they did a couple of pre-tests whether the kids think that these are real people or not. So I mean, I would trust them now that they do not do the study with 100 children over the last 4 months or 5 without thinking that this gives them the a real answer to their question. But I'm not a social psychologist, so I can't say. And I see from a layman's perspective, yeah, there might be some co-founding variable in it, which is stronger than all the explaining variables.
Okay, more questions from the others? Yeah.
For example, for 2D images with pixels, you can sample it differently than you use hexagons, for example, which is often done in print. Could you easily then also map this probably to 3D, that you use then some sort of three-dimensional hexagons instead of your normal things? Would this work better because you would have better interpolation? Or like,
Yep. I understand your question. I think I had a similar question at ISMA. Probably yes. I think we could improve the visual quality by using different geometries per voxel. And we haven't tried it. Perhaps we just have to implement a different shader and then give it a go. It's actually a good point. Perhaps we would do that. It's actually easily done. Yeah.
There's lots of different options in point-based rendering. Of course, use different point bases and also splatting for also rendering. You could use splatters that blend better, so you don't need a geometric precise correlation of the different splats. So splatting you could do. You could use splatting. I mean, if you have a good, estimate, you get the depth and you know how big the splat size would be. So you get that, but you get also some fringe problems with the splats as well. So I mean, it needs to be tested. Actually, I don't know. Probably won't have the time. But I saw it with, for instance, Bernd Fröhlich does that with his, with his big data sets, and they use splatting entirely, and so we could also use their implementation to test it. Yeah, that's a good point. But what I want to repeat, that it is actually, it's probably what we try to do is we test the less is more approach, right? So the simplest possible solution, also in terms of computation, which can be used to produce a believable experience, and we will see how far we will get with that. That's the question. And there are a couple of things we will certainly try to control the fidelity of the scene in both ways. So less and more. Yeah. There's actually also some approaches like what Jan Fischer did, so with video see-through augmented reality. So to stylize, both in environments, let's say the real world with video as well as the virtual content in the same way. So it's actually the same idea. So you degrade both realms to get higher coherence, and that also in terms of simplifying and perhaps also highlighting, or perhaps you can direct attention or whatsoever. So we are in the very beginning of that kind of testing process. Good. More questions? Once, twice. Thank you, Holger, again.
Thank you very much.